Look at this sequence of 19 images. It shows how Earth appears over a full 24-hour period. Well, these images weren't actually taken from the Moon, which is 400,000 kilometers away. Instead, they were captured by the Discover satellite from a distance of 1.5 million kilometers, about 3.5 times farther than the Moon. But even from the Moon's surface, Earth would appear quite similar, a rotating blue and white sphere drifting through space. Now let's reverse the perspective. How does the Moon appear from Earth? In this time-lapse video, each second represents one full day, and every second consists of 24 frames, so each frame corresponds to an hour of real time. Do you notice something strange? The Moon doesn't seem to rotate. Sure, it wobbles slightly, but it doesn't appear to spin on its axis the way Earth does. Yet we know with absolute certainty that the Moon does rotate on its axis, completing one full rotation every 27.3 days. So why can't we see this rotation? Have you ever wondered why we always see the same face of the Moon? How does this happen? And what's on the so-called dark side of the Moon? Are they hiding something from us? Let's dive in. At first glance, it might seem like the Moon doesn't rotate at all. However, the truth is that the Moon does rotate on its axis. It just does so in perfect synchrony with its orbit around Earth. This means that as the Moon orbits Earth once every 27.3 days, it also completes exactly one full rotation on its own axis in the same period. This phenomenon is called synchronous rotation, or more commonly, tidal locking. Tidal locking happens due to the gravitational interactions between the Earth and the Moon. Over millions of years, Earth's gravity acted as a brake on the Moon's rotation, slowing it down until its rotation period exactly matched its orbital period. This is why we always see the same hemisphere of the Moon, while the other remains hidden from our direct view. To better understand this concept, let's use Universe Sandbox, a powerful simulation tool that lets us visualize celestial mechanics in real time. By inputting accurate data on the Moon's rotation and orbital speed, we can see why the same hemisphere of the Moon always faces Earth. We can also tweak the Moon's initial conditions to see what would happen if its rotation were slightly faster or slower. Spoiler alert, it wouldn't remain tidally locked. Universe Sandbox also allows us to model what would happen if Earth's gravity were weaker, or if the Moon had started with a different rotational speed. This kind of interactive visualization helps us grasp why tidal locking is not a coincidence, but a predictable result of gravitational forces over long timescales. Contrary to popular belief, the far side of the Moon isn't actually dark. It receives just as much sunlight as the near side. The reason we call it the dark side is because it was unknown to us until the era of space exploration. The far side was first photographed by the Soviet Luna 3 probe in 1959, and it looked strikingly different from the near side. Unlike the familiar side of the Moon, which has large, dark Maria lava plains, the far side is heavily cratered and lacks these smooth plains. Scientists believe this difference is due to variations in the Moon's crust thickness, possibly influenced by early tidal heating and impacts. Today, we have detailed maps of the far side thanks to missions like China's Chang'e 4, which even landed a rover, Yutu-2, on the Moon's hidden hemisphere. This ongoing exploration helps us learn more about the Moon's mysterious past and its asymmetrical nature. One of the biggest mysteries about the Moon is why its near and far sides look so different. The near side, which we always see, has vast dark lava plains known as Lunar Maria. These were formed by ancient volcanic activity. Meanwhile, the far side is densely packed with craters and lacks these large plains. Scientists believe that this difference arises from the Moon's early history. The leading theory suggests that the near side had a thinner crust due to Earth's gravitational influence, allowing more volcanic activity to resurface and fill in craters. The far side, in contrast, had a thicker crust that prevented magma from breaking through, leaving it heavily cratered and rugged. Even though the moon is tidally locked, it doesn't appear completely motionless from our perspective. Instead, it exhibits a slight wobbling motion called libration. This allows us to see up to 59% of the moon's surface over time, rather than just 50%. Libration occurs due to a combination of factors, including the moon's slightly elliptical orbit and the tilt of its axis. There are three main types of libration. Libration in longitude, caused by the moon's varying orbital speed around Earth. Libration in latitude, due to the moon's axial tilt, allowing us to see slightly above and below its usual visible area. Diurnal libration, a small shift caused by Earth's rotation, which slightly changes our viewing angle each day. The reason behind this fascinating phenomenon is gravitational interaction. Earth's gravity exerts strong tidal forces on the moon, creating a stretching effect that has gradually synchronized its rotation with its orbit. Over billions of years, these forces acted as a natural brake, slowing down the moon's initial faster rotation until it matched its orbital period. This process, known as tidal acceleration, still continues today, though at a much slower rate. In fact, the moon is slowly moving away from Earth at a rate of about 3.8 centimeters per year. Tidal locking isn't unique to the moon. Many moons in our solar system, including Jupiter's Io, Europa, and Ganymede, as well as Saturn's Titan, are tidally locked to their parent planets. Even some exoplanets, especially those close to their stars, are thought to be tidally locked, with one side experiencing perpetual daylight while the other remains in constant darkness. If Earth were to get closer to the Sun over millions or billions of years, it too could become tidally locked, always showing the same face to the Sun. The fact that we always see the same face of the moon is not just an interesting curiosity, it's a direct consequence of fundamental physics. Understanding tidal locking helps us make sense of not just the moon's motion, but also the behavior of other moons, planets, and even distant exoplanets. Everything in the universe is connected through gravity and motion, shaping the celestial ballet we see in the night sky.